Okay, so last time we were talking about geometric rectification. So what happens in this context is we have a particle, in this case in the channel. So the channel is left-right asymmetric. And if we think about a Brownian particle, a passive particle, if you put that into this channel, on average, they're not going to go anywhere because it's in equilibrium. However, what happens if you have active particle is, remember that we derived a relation for the average velocity along the channel. So that's given by the net diffusive flux, which means if you have a density gradient in the horizontal direction, that's going to drive a velocity. So here's a calculation with that result. So if you look at the average net velocity normalized by the swim speed as a function of the activity, we see you have a non-zero velocity, and it has a dependence on how active you are. So that's in the channel which has no flow. So then we set out to talk about what happens when you have flow at the end of yesterday's lectures. So what we see here is experiments of E. coli solution between two vertical plates in a channel. So on the left, there's no flow. Okay, so they're just undergoing their random active motion. On the right, there's a systematic flow that's coming from the top to the bottom. So what we see here is many bacteria are going against the flow. Yeah. So we can model this, try to understand this physically by making use of our model that we talked about extensively, making use of the active Brownian particle model. Again, we can write down the same conservation equation. So the only difference now when particles are placed in a flow is I'm going to get these advective fields due to the flow. So in the linear space, I have to be moving along with the fluid velocity. Similarly, I get an angular velocity due to the shear of the flow. So I will rotating by following the fluid angular velocity. And we talked about this last time. So initially, so suppose I can do a Brownian dynamics simulation, except that I've turned off Brownian motion entirely here to demonstrate the trajectory. So you can do that easily on a computer, not so much in real experiments. So here, initially I placed a active particle that's pointing towards the upper wall. So what happened here, as we talked about last time, is in the linear space, so that's the green trajectory. That's the trajectory of the particle position. So it's being advected downstream, but at the same time moving up because of swimming. So it gets to the wall, and what happens next is this particle is again constantly being rotated by the fluid angular velocity, and eventually you get this interesting trajectory. And the point is, in this case, the particle is going upstream on average. Okay? And here's an experimental measurement of a bacterial. This is not a bacteria. I think this is a sperm cell in a channel flow. So initially it started here, and you see that it exactly tracks out this kind of a trajectory. So it's hopping between the two walls in order to go upstream.
So it's
Questioning.
here is common. It is
Which is common?
it is upstream.
Yeah. So this is common because but essentially when you have activity, this can happen. Of course, there are parameters that dictate the dynamics. For example, if your flow field or flow velocity is much higher than your swim velocity, you can imagine you're going to just be dominated by the flow, and in that case, you cannot swim upstream. So there's a critical ratio between the swim speed and the flow speed, which we'll talk about later in a few slides. But it's a general phenomenon. Because the mechanics we talk about here is universal, right? Regardless of what kind of particles you have, you would follow more or less this kind of dynamics. Other comments? Okay, that's good. So here's a simulation that we looked at last time. Just active Brownian particles. In this case, the flow is turned off. Okay. So when you do a simulation like that, they're going to equally likely to go left or right. And we also talked about how particles are going to accumulate at the wall because they're stuck there for a long time. And what happens if you think about a particle at the wall? First, the particle has to be pointing towards the wall. Otherwise, you can swim away. So it's stuck there. That means it's pointing more or less upward. And then if you look at the flow, so the fluid velocity at the wall is 0, but the gradient is the maximum. Okay. And in that case, if you think about the angular velocity of the fluid, it's precisely turning the particle towards this direction. Now, if you are turning this direction, you're still swimming constantly, and then you're able to go upstream, okay, by projecting your velocity into the horizontal direction. So that's in the case of no Brownian motion for a simple demonstration of how it swims upstream. So if you have Brownian motion, so we want to bring, yeah.
You're subsidizing the which has a finite amount of food.
Infinite amount of, yeah, 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 that's correct. Yeah,
It's the initial condition practice.
yeah, yeah.
Over there, we consider that like only consider the dynamic.
And what else would you?
So, on the fact of the fuel, we're considering that. So
Yeah.
Thinking that the fuel is infinite.
Yeah,
We're just focusing on the
that's correct.
dynamics.
And that's almost always the case, as you can see here in this experiment. There's no fuel here. You just put a sperm in water. They can do this. And in this case,
Also, like actually, we have it. If you observe it, it's like the time scale. There's like fuel is not chill. They
Yeah.
still have this.
yeah, you can see here with this. Yeah,
That is typical.
yeah. So in this case, this is about 100 seconds. So this happens quite fast, and they really traverse through quite long trajectory. So this, if you look at the scale bar here, this is 100 hours. So almost never you worry about the fuel depletion, unless again it's a very dense colony of bacteria, and then they're competing for resources. Usually that's not the case.
Because when they come to rescue you,
Yeah.
to as a global event. So
Yes, but yeah. But if you think about infections and things like that, there's a few of them. There's not gonna be a very dense population of them. Actually, getting a dense population requires special experiment procedures. You want to culture them and make sure there's a lot of them. In general, it's quite that in system that you find in nature.
you see,
Other comments? Yeah.
In the next time while doing the simulation, the initial condition, what file do we set?
So in this case, initially the angles are randomly uniform. Again, that would not matter if you're looking at the long time behavior. Of course, for the very short times, there's a difference.
So like in terms of like the smudges, keys,
Yeah.
So like for mean spread, especially we say that it just goes from here to there.
Okay.
So you think from like already perspective, how do we say the
sure that it's instead.
Yeah, we saw the Chomsky equation. How do we say that? Yeah.
I'm just saying usually is spreading like
Yeah. So if you want to solve the transient problem, okay, like the problem we talked about the ballistic to diffusive transition, then you want to set the equivalent initial condition in the smooth Chomsky equation as well. For example, you have a randomly uniform probability in orientations, then the probability would be, suppose you have a delta function in space, so localized in space, but the angles are randomly uniform, then you would have an initial distribution of 1 over 2 pi. That's the angles times the delta function in x. Okay, so that has to be the same as compared to the Brownian dynamics. You want to match them for time-dependent dynamics. But if you only care about long time, then you don't. It doesn't matter. Yeah. Other questions?
And philosophy the thermodynamics, the flow is augments only swimming speed is present.
The flow is.
All it's only swimming.
Yeah. So in this demonstration, the flow is turned off, so it's just particles in stationary fluid.
And then also the area are randomly arranged, but not sorry, that air maximum maximum accumulation is up to inches.
At the wall. So they wouldn't accumulate in the middle, because when you think about accumulation, the only reason they accumulate at the wall is they're trying to swim, but they're stuck there. Right? So any place in the middle when there's no boundaries, you're not gonna stop there, so they're not gonna accumulate. Which means
Orientation is completely random.
orientation at what location? Are you talking about the initial condition or?
Right.
This one is
So here, the orientation is not random. There's a bias because of the wall. The point is, if you are pointing downward, for example, if you're here pointing downward, you're not going to be there. You swim away. The particles near the wall actually has bias in their orientation. So on average, they're more likely to be pointing upward due to the boundary presence of the boundary. Does that make sense? Because otherwise, it will swim away, right? Yeah.
yes, that's also the scene something just like this, right?
Yeah, this is the same video that we looked at yesterday.
So it's the same.
Yes, exact same video.
Sure.
because of the rotational motion of the particles, right? Because it has a persistence and it rotates, but when it rotates, it has a direction towards the wall.
Yeah.
It has persistence, it sticks over this. But
Yeah.
when it rotates in this direction is towards the wall.
Yeah,
It sticks towards the wall.
that's right.
That is why there is a bias towards.
Yeah, because because of the wall was going to cut off part of your, or you can't go that way.
So flow out means that thermodynamic per time.
So there's no advection in the fluid field. It's completely zero. It's just the active particles on their own.
Yeah.
In a stationary fluid.
That is just a swim, but
Yes, they're just swimming and diffusing.
whenever there is a flow or there is a kinetic, like gravitational force per term of this.
Yeah, when you turn on the flow, turn back flow on, then you get the advection fields again. Yeah, which is what we're gonna think about next.
So when we think about longevity treatment, we still have the friction because the fluid right?
Yeah. So you're always in the fluid medium. You still have the friction. You just don't
Look, they have
at the vector velocity.
Yeah.
And that's how we move in general.
Or just
When as humans, we walk, there's friction.
nothing.
If there's no friction, you can't walk.
It's reduce.
So now we want to bring back Brownian motion and think about how do we use our equations to understand how it behaves, right? In this case, so turns out this is a classical problem due to G.I. Taylor, which is a British physicist and fluid mechanician. So at the time, Taylor was looking at precisely particles in a flow like this, but passive, okay? Brownian solutes in water, and there's flow going from left to right. So what he discovered is that if you were to measure the long time mean square displacement, you can track the mean square displacement only in the longitudinal direction, okay, as a function of time, and then you can characterize the slope at long times. What he discovered that is the diffusivity of long times again is not equal to the molecular diffusivity. Keep in mind, in this case, there's no activity, just passive Brownian particles.
you think the Brownian diffusion.
Yeah, yeah. Okay, so it's higher than that in the case of flow. So that's a very interesting phenomenon. So here's an interesting cartoon that we can use to understand this process. So imagine again at time 0, I'm going to have a patch of Brownian particles somewhere in the channel. I don't care about the distribution. Here I've taken a band of not swimmers, band of Brownian particles here. Now if you think about short times, notice that the fluid velocity at different y locations are different, okay? Which means these particles, again, they're following the fluid velocity, but at different locations in y, they follow a different fluid velocity. So what happens is the density profile is going to look like this, because in the middle, you've moved furthest to the right, okay? Whereas at the wall, you haven't moved much due to flow. So what happens, because of the flow, the concentration profile is distorted now. You create these void spaces where there's no Brownian particles. What does that mean for the density? So it means there's a density gradient in the y direction, okay? That's created by the flow. Does that make sense? That's the first key observation. Well, these particles have their own Brownian diffusivity. If you have a density gradient, what happens? That will drive a diffusive flux. So in this case, on the left, it's going from top and bottom to the middle, whereas here, there's particles here, but nothing here, so you're gonna diffuse outward. So you're spreading in the transverse direction. And and then this is the intermediate scheme where it's being more or less smoothed out. So what happens at long times is effectively you actually have more spreading horizontally, even though the diffusive flux is in the vertical direction. So when you couple that to the fluid advection, you have more spreading at long times compared to if you just have molecular diffusion. So mathematically, we can describe this process. So there's two things we have to describe. The first is what is the average velocity that these particles have. So we talked about that before in the case of rectification and other contexts. So as you might have guessed, these are passive particles. So the average velocity they get is just the average velocity of the flow field. The reason that you have to average the flow is because, again, at each location, you're getting a different fluid velocity. Then on average, particles follow the average fluid velocity in the y direction. The fluid doesn't change in x, okay? So that's the average velocity. But then the next point is, what is the effective diffusivity at long times? Again, we can model this by a random walk. So essentially, particles is going to take a step in the x direction, okay? How do they take that step? Because they're passive, the only way to take that step is they follow the fluid velocity, okay? But there's a time scale associated with this random walk, and that time scale is this diffusive time scale. How long does it take for the particles to migrate in a vertical direction? That's given by the size of the channel squared divided by the molecular diffusivity, translational diffusivity. So if you take L squared, as we did before, divided by tau, what you get is this relation. And if you make this dimensionless by comparing the effective diffusivity to the Brownian value, you get a Peckley squared scaling, where a Peckley number essentially measures the relative importance of the fluid velocity compared to Brownian diffusion.
If it's still what to see with.
That's the typical fluid velocity in the channel. So you can take that as the maximum or the average. Yeah, it doesn't matter in the case of a scaling argument. Okay, so that's a very interesting result. Any questions about this?
So, yeah.
PE.
That's the basis quantity. It's the fluid velocity size of the channel divided by the Brownian diffusion.
So, okay, that's tau.
Tau is here.
Then when can we d effect 2 by d cumulatively?
Yeah, so we have first time we have this relation here, right?
Where d effective is L squared over tau, and then I'm going to plug in L and tau. The next thing I do is I divide this d effective by dt. Then I'm going to get a dimensionless quantity out of on the right-hand side by grouping all these things. So that turns out to be this Peckley number squared, which is a dimensionless quantity in the system.
And
What is the signal?
theory for active mathematics that we will have been thinking about
Is it
for
the
years.
with in
And what we've seen before,
Yeah,
so you're comparing the long-time diffusivity to the Brownian value, right?
It's not one. So that's the point of what we started to talk about this. It actually depends on the fluid velocity. So the effective diffusion you measure at long times is a function of the flow because of this process that we described here. Whereas if you don't have flow, what is d effective? It's dt. So that's the point of this exercise. Because of the presence of the flow, that will actually modify the long-time diffusive behavior in the system. Other comments?
So basically, no all condition.
Yeah, flow is here. Flow is present.
Okay.
Yeah. But activity is not. And we're talking about passive system. And now we'll think about what happens with active matter. So the only thing I want to do now is to replace this passive Brownian particles with active Brownian particles.
So after the flexibility law saying that actually we follow the relativity program.
Yeah, on average, yeah. Because I'm just a passive particle being carried away by fluid flow.
The activity.
There's no activity here. Yeah, it's passive. Swim speed is 0. Other comments? Okay, good. So what about active systems? So we can generalize this theory that's been developed by Taylor and later on by other people. Okay, you can read all about this. This is called the macro transport processes. So in other context, this is a homogenization theory. So the point is, so this equation now looks familiar. We looked at that yesterday in free space. So essentially, you can write down an effective advection diffusion equation. Here, this rho hat is the density, the number density. And in this case, you only write that equation in the longitudinal direction, in the x direction. And then you only have one wave number, k, instead of a wave vector. But nonetheless, that's an effective one-dimensional advection diffusion equation. And again, you can read off these coefficients by looking at the coefficient that's proportional to ik, that's the average velocity, and the coefficient that's in front of k squared, that would be the effective diffusivity. So in this case, when we have flow and activity, again, we see two contributions to the net velocity. One is I'm swimming, so there must be an average velocity due to my swimming motion. The second, we've seen already, that is the fluid velocity, but averaged against the particle density distribution. In the case of a Brownian system, what's the density distribution at long times? That's uniform. So that's why we get just the average fluid velocity in the previous slide. But right now, we have two terms. One is the polar order along the x direction, the other is the average flow velocity weighted by the density. So the diffusion, again, has a few contributions. The first term we know already, That's the translational Brownian diffusivity. The second term we've seen again before, so that's the fluctuation in the swimming motion. That's m tilde, that represents the fluctuations. And similarly, as you can imagine, in the presence of flow, there's a fluctuation in the density. And that's again weighted by the flow, so that gives another contribution. So now there's 3 contributions. And now if you again think about the case we looked at in the previous slide, where the swim speed is 0, then we don't have the second term, right, in the diffusivity. We have 2 terms. One is the Brownian term. The other is the fluctuation in the density, which is the origin of what you get in the passive case, where you have elevated long-time diffusion. That's because the flow induces additional fluctuations in number density.
Yeah. If you mean the translation is happening in all directions, that's the topic. Yeah, because y is confined. So at long times, what's the mean squared displacement in the y direction? That's a constant. Because the most you can get in y is h. So it wouldn't be diffusive at long time. And the utility of this is when you think about traveler's motion in a tube, you're not worried about the vertical, you're worried about where to go along the tube. Yeah.
The other question is like this diffusion, I think it's diffusion.
Yeah.
So like usually I'm gonna understand why is this negative sign, but
On the sign, it has no significance whatsoever. You could have defined your Fourier transform. There are 2 ways to define Fourier transform. One is e to the IPX. Y is e to the minus IPX. There's no significance in the sign whatsoever. So if you write it other way, the sign will go into this n, and here it will be plus. Okay, so that has nothing to do with physics. It's just a notation. Yeah.
like, obviously when we're considering G is model different.
Yeah.
But the very significance of why this all came to.
So that's a very great question, actually. So if we think about
General conservation laws, in the real space, okay, what we write is we write partial whatever quantity is conserved, partial t plus the divergence of a flux equal to 0. That is always true for a conservation law, okay? That's the first point. The second point is now, well, for different systems, you need to tell me how do I write down the flux vector, and that's a constitutive relation. And in general, the flux vector has many terms as the drift, the average velocity due to advection, you can have diffusion, you can have higher order gradients. Okay, in general, that's allowed. And the reason that we normally don't talk about higher order gradients is we're saying, okay, essentially higher order gradients are weaker, say, than the second order. So we truncate after the second order. Okay, so that's how we write down the advection diffusion equation in real space. So we've neglected other terms. So if you just think about symmetry from physics, it doesn't say you can't have higher order terms, such as the 4th order derivative, right, in the flux vector. However, what we do is we call the term that's proportional, or the linear term, the advection field, and the quadratic term, the diffusion. And there are names for higher order terms, but they do not contribute to diffusivity, because diffusivity is defined as the 2nd order term. So if you are talking about mean square displacement, that's what you're looking at here. But you can look at the 3rd, x cubed, okay? Then you appear here, or x to the 4th power averaged. But normally we don't worry about those higher order moments.
It's not like say we are considering the mean square is with
Yeah, so this only characterizes the mean and the mean squared.
deviation.
That's correct. But if you think about probability, you have higher moments. You have kurtosis and whatever. Yeah. So you can do that. Then you would include those terms. Okay, does that make sense? However, here, if you are only caring about the drift and the diffusivity, this is an exact calculation. These terms do not contribute to the diffusivity. Okay, so that's also an important point to note. Any other comments about this?
Yep.
I'm just glad we can. It's the
Density of particles. Yes. That's correct.
And
The That's so the substrate is the average density.
You do an average over the
Yeah.
spheres and
And
you
the symbols with the tilde, that's the fluctuating quantity.
that tells you how
Fluctuations. That's you can think of it as the mean and the
pressure
the
rating
average of the mean minus the actual quantity. So that's yeah.
the big
Think
thing
about
was
what happens when we
Yeah,
add
that's the average speed these particles are moving
I
at.
think this is a question.
And
Sorry?
when we add this,
You effective
Yep.
average
That's the average velocity of the particles.
if in presence of
So if
equation.
you take
That's correct.
So you are just taking care of us, so ubiquitous thing.
Yeah,
And
in this
this
equation, we have
average you
this
That's
is
the flow
current,
part.
right?
because I also have to follow the flow.
and what you say what is rho naught?
That's the average density.
And
Average
we have
density.
the
Yeah.
active term.
Okay, and you is L
Flow field. That's fluid velocity. Yeah.
and
Friction.
okay. No son
So,
is a
If
why
you look
you are
at
not
these two
consuming
terms,
higher
the
volume
first one
units?
is the
You can, but that
This
wouldn't
is-
contribute to the diffusivity.
on
It would
fluid.
contribute to the third moment and the
And
fourth,
other is
and
the
so on and so
friction.
forth. But the diffusivity is
So you compare
defined
these terms, you can
as
introduce
the
a new parameter
mean squared
called
displacement,
the
right?
length
That's the
scale
derivative of the mean squared displacement
here.
over
Okay,
time.
let's define
So I
length
know the
scale
question
L.
Yeah.
that it is turnover level. So obviously the
By just
average
balancing these
because
terms.
it
Now,
can
the
solve
left hand
average stupid average stupid.
We
Yeah.
have the viscosity.
Is that just
We have the
Yeah, so if you so
Right.
essentially these are moments in
Length scale
language of
squared.
probability. If you want to get
And
more
have the velocity,
detail about
which we can-
the probability distribution
So,
function,
is on the
right, you
right,
can
so
consider higher
velocity.
moments. So these
So then,
these
if we
average
balance these
driven
terms, we can derive
diffusivity again only gives you the
length
mean and
scale
variance,
L,
nothing more.
which is given by the square
So you have
root of
limited
gamma.
information about the distribution. But the
Square
point here
root
is
of
we don't really care about the distribution
gamma.
per se. We care about
Right?
whether
So
and
it's
only and
using
how fast they're
new
spreading
personal
in
length
the
scale
context of
system.
real problems that we want to know about. But of course, mathematically, you can continue, and then you can get the full distribution if you want that way. Yeah. Other comments? Okay, so we have these equations and we can solve them. So in this case, there are two ways you can solve these equations. One is simple, which is just doing Brownian dynamic simulations, as we did before, and then you just measure the velocity and the diffusivity, okay, by tracking the mean and mean square displacements. The other is solve this theory that we developed. And here is a plot of the average velocity of the particles. In this case, it's scaled by the average velocity of the flow. That's the y-axis. In the x-axis, that's the Packer number, which measures essentially the flow speed, so how fast the flow is going compared to the particle's Brownian motion. So you can look at that as an increase in flow speed, okay, from left to right. So what happens for passive particles when I again turn off activity? What is this quantity?
So what?
It's 1 because we've discovered that the effective velocity is the flow velocity for passive. So I've scaled that out. So that's flat, horizontal at 1. Doesn't depend on Peckley because that's already included here, okay? And for active, we see an interesting behavior, okay? So for when the flow is small, you have a negative velocity. Negative means going to the negative x direction, so that's upstream.
Average over the bar, that is
Yeah.
that is the average in the y direction of the flow.
That's right.
That is the constant, right?
That is a constant.
The other thing is here.
And
notice that also
if
the
we think
units
about this region where the flow speed is
and
very
just have a
high,
very regular
so if you think about the case where the flow speed
line in one direction,
is much
it
higher than the
doesn't
swim
stop.
speed,
So that's one way to
as someone observing the system, can I tell that these guys are swimming? I cannot, because the flow is going so fast, which means necessarily that if you measure the average velocity, I should get back whatever the passive result is. So that's why you see as the effect when flow speed decreases, you're gonna go back to the passive result. However, as you lower the flow speed, you cannot tell that these particles are not passive because they're swimming and their velocity perhaps is smaller or comparable, or in this case even larger than the flow velocity. So in that case, they can go upstream. And the best chance you get in going upstream is when your flow velocity is small. But notice here the x-axis is on a log scale. So here the fluid velocity is not 0. Okay? So if the fluid velocity is precisely 0, what do you get for the average velocity?
So even if it's initially
If I can turn off the flow,
and
so
introduce
there's no bias, so it will be 0. So the point is, you want to have fluid with flow,
surface, and actually
weak
what
and
happens
not too strong, but you can have a zero flow you wouldn't get a bias motion in the horizontal.
Usually just to be having a lot. So
bias was inside.
That's correct.
So, but if we point the US, like US thought changing for the
The exchanges. That's right.
and this is the one fixed essentially.
Yeah. So the only thing I'm changing here is the flow speed. Everything else is fixed. Yeah.
So here you have we can do it for different upstream speeds.
They will draw a different part and it's something like this. Okay. Yeah.
So what will be the intuition for the range those
Different flow speed. So if you pick a particular flow speed, you increase the swim speed. Either in this region, you get more velocity upstream. Okay, so that's what happens in that context. Of course, here doesn't matter. Again. So as your flow is very strong, it's gonna overcome the activity. So
speaking.
other questions?
so
Yeah.
the previous question.
The equation, yes.
So now that it's in the algebraic number.
Here,
Yes.
here now, here the density is don't depend on the wave numbers. I've already Taylor expanded to either the average. The wave numbers are explicitly written outside.
Yes.
So they're both have to depend on the wave number precisely. Yes.
I can understand about the what is real like having the X there.
Oh yeah, then you have solved this equation at short times, which I haven't done yet. So the only thing I've done is taking the limit as time goes to infinity. I only solved the long time behavior. So in yesterday's lectures, we looked at the wave to diffusive transition. In there, you solve the full equation over time. Okay, from initial condition to long times. Here, I've only looked at the long time behavior. Does that make sense? Yeah.
When we say that this equation is that is for with numbers.
So this is not valid for the initial transient behavior, because you can imagine initially let's have a delta function distribution of particle density. That's an arc wave number. So this only works for long times.
This is start wave number. For small wave number is a wave gradient. Wave number is what? Is a variation over length space. So which means the density is small, or the variation occurs at a very large length scale. So that only occurs when the particles are moved very far away. So that's a long time dynamics. Yeah. Other questions? Okay, so coming back to the spot here. Let's look at a video from Brownian dynamics simulations. At this location, okay? What do you see? You see more particles going upstream than downstream. Again, these are dilute systems. When you say more particles, that's just here to provide the statistics, right? So this means it's more likely to go upstream in this location.
We see more.
Sorry?
Why particle?
It's one particle. Essentially, it's one particle, but you don't want to run a simulation for one particle. You run many of them, but they're completely independent. Okay, and then you can overlay them here. Then this density gives you the probability density, right? Okay, great. So let's look at this region where the fluid velocity is much higher than the swim speed. Again, if I'm looking at this system, I shouldn't be able to tell that these guys are active. And you cannot. They're just following the flow, going downstream. Okay, so that's agrees with our intuition. Okay, any comments about these simulations?
My question.
Yeah.
It's a still real like bricks.
I'm gonna talk about the real life situation later on.
So maybe the speed is generally smaller.
No, it depends.
But still behavior also.
Should be smaller than the swim speed. Okay. Yeah.
And then when you at this very very small, you see that over the on the outside.
When the flow velocity is small, yes.
So A is somewhere there.
Yeah. But it's still negative, right? So essentially, if you're looking at here, then more particles are going left and faster. Yeah.
And if you go a bit
Below here, yes, it's the same behavior. It's just
so but why do you actually think that it's little particles over there, right?
here, it's because of the scale, the funny scaling, because this every fluid is velocity also depends on magic number.
Okay.
So actually, the dimensional quantity vanishes when pathway goes to 0, but you scale that out. So that's why there's a path L, right? If you scale the average velocity by quantity, it does not depend on the packet number, that this will go down to 0. When packet goes to 0, there's no flow.
So largely,
Yeah.
You can see
at
it
the,
from
at the
here
current
from the
stage,
negative.
it's just trying to
It jumps up to 0, right?
experimentally
What if it shows up?
design systems
Take when it
to
comes to 0.
understand
And
active
this thing,
physics.
take when
In
it
terms
comes
of
to
the
Yeah.
application, right now, there's not much. And
the effective
previous
thing,
work largely trying to
Yeah,
understand
that's a singular
the,
limit. So long as there's flow, as a singular limit, we think about the perturbation or tiny limits there. Yeah.
It's mostly the
Okay,
flow,
great.
the structure of the turbulent flow and the connection. The
So
question is,
essentially, okay, so
because
the
this is
simplest
not
region
actual
is
turbulence
again
that we're
the
familiar
ground
with,
locus,
but
where
the-
you can't
Really tell apart that particles are swimming, and only when the case where the flow is weak, particles behave differently compared to the passive case. So that's great. So that's the average fluid velocity. That's the average drift. And again, we set out to think about the diffusivity of long times. And so here I'm again looking at the effective diffusivity of long times normalized by the Brownian value. Okay, as a function of the flow speed. So we have the passive result we talked about before. So when the flow is high, there's a quadratic scaling, right? So when the flow goes down to 0, what should this value be in y? So when you turn off the flow, the diffusivity of a passive particle is just the Brownian value, right? So you should go back to unity. That's 10 to the 0 on the left. And as your flow becomes faster and faster, you get more and more spreading for passive. This is a passive system. All right, that's the formula we discussed earlier. So here's the result for an active system. Again, one thing we can understand right away by comparing to the previous slide is this regime. This regime is where the flow is very high. Again, I can't tell whether these guys are swimming or not, which means I should track the passive result in that regime. Okay, that's good. Now let's look at the left regime where the flow is going to 0. So when flow is completely turned off, why is the diffusivity of an active guy larger than the passive? What's the reason for that?
Any suggestions?
Because of the swim diffusivity that we introduced earlier, right? So, well, your particles are in your channel, flow is turned off, you're still undergoing this random walk. So you still have elevated diffusion compared to the passive. So that's why you will start at a higher value. Eventually, you will track this curve. But the third interesting behavior is why does it go down first before it comes back up? You could have just gone this way, right? But it did not. It decreases before it increases again. Okay, so that's a very interesting behavior. And we can again understand that with our theoretical model. So if you think about our equations in the diffusivity, so if we go back there, notice we have this term here. That's the swim diffusivity, right? The fluctuation in the swimming motion. But because you have flow, particles cannot just take their free run length anymore because they're influenced by the flow. The flow will turn them faster or slower depending on how fast the flow is. So effectively, their step length is going to be affected by the flow. So if we go back to this plot here, so essentially, question, yeah. So if you think about an active particle that's swimming around without any obstruction, then you can take your full step. But now you're in a flow which has an angular velocity. So what does the angular velocity do to a particle? It spins them. You have more spin now. If you spin more compared to the case where you don't have flow, what's your step length? You're trying to swim, but you're spinning too fast, so you can't go anywhere. So effectively, your step length is going to decrease as the flow becomes faster. Well, if effectively your step length decreases, your swim diffusivity under the influence of the flow is going to plummet as a function of the flow. Okay, so this vorticity or the angular velocity of the flow is going to reduce this step length. Then you can plot what kind of diffusivity you get from this reduction. You will plummet. Okay, so that's the swim diffusivity contribution, the second term in the formula. There's the third term, which is the fluctuation in the density weighted by the flow. That's always there, regardless of whether you're active or passive. So then the point is, why don't you add up the red curve and the black curve, what do you get? You get the blue one. So there are computational processes that's happening. And in this regime, this swim part is completely shut off. And that's why you recover the passive. Whereas in this regime, there's no flow. So I just have the active diffusive process. So that explains completely why you observe this kind of non-monotonic behavior in their diffusivity. Any questions? Okay, great. So we understand this system theoretically in a quite extensive fashion. The question is, what's the point about this? So here's an experiment. On the left, what you have is two reservoirs, okay, connected via a tube. There's water in the reservoir and the tube. That's all. And you're gonna flow fluid from the top reservoir to the bottom. Okay, that's the first condition. Secondly, I'm going to place some bacteria in the bottom reservoir. There's no bacteria at the top. Okay, just in the bottom, and the flow is coming down. So from our theory, what's going to happen? So this bacteria is going to go upstream, right? They're going to migrate if the flow conditions is favorable. So that's what we see here in these images. So you should look at this from the bottom to the top. So this is after about 15 seconds. What you see is these white trajectories are the bacteria motion. Bacteria trajectory, you're seeing some of them are climbing up by going against the flow. And here's a zoomed in image of looking at essentially in this inlet here, the bacteria you see, they're going up. And some of them has fallen off, but some will continue going against the flow. And here, this is after 15 minutes, some bacteria has already moved to the entry of the top reservoir. Okay, that's after about 15 minutes. So you see, indeed, in real systems, bacteria is going to migrate against the flow, as we have talked about in our modeling. So why is this interesting? So this is interesting in the context of, for example, catheter infections. So in patients with catheter implant, this kind of infection happens quite a lot. Even though when you think about when you place these devices, they're all sterilized. Okay? So what happens here is you have urine flow coming out of the tube into this bag. Okay? This bag is stationary. Okay, it's gonna sit there for a day or so, depending on the protocol of the hospital. But nonetheless, in the stationary bag, bacteria can develop, and once you have bacteria in there, when you have flow coming down, it's going to migrate upstream and gets into the urinary tract, which will cause infections. Okay. So what can we do? From what we've learned so far, we've learned two things. One is active particles placed in a corrugated channel, an asymmetric channel, is going to have a net flux going somewhere. Why don't we make use of that in this context? Why don't we make these catheter tubes with some interior protrusions that will sort of deflect these guys towards the downstream so that they don't come back up, okay? That's one thing we can think about. But in this context, it's more involved than that because, well, we can make this kind of a channel easily, say by doing a 3D printed channel, but we have flow here, right? In the rectification, we just have active particles without flow. So there's additional complexity. So let's try to do a simulation, again, of a single particle. In this case, there is flow present, which is not shown here, but there's flow, and the particles is swimming, okay, in this kind of a channel design. What you see here on the left, you see the teeth is slightly tilted towards the right, but not too much. You see initially the particle is stuck here for a few cycles, but eventually it's going to slide off this teeth, and then it just hops onto a different trajectory, and it's still migrating to the left, which is the upstream. So in this design, we have failed to prevent them from going upstream because the teeth is essentially not tilted enough. So on the right-hand side, it's a different design where you see it's more tilted. And what you see here, again, in these simulations, the Brownian motion is turned off, so that we can see their effects just due to the flow, and they're swimming. In this case, they're stuck in a cycle here. If you think about it, when the bacteria coming down from here, it's sliding off, but because the teeth is pointing to the right, So you will go into this orientation, and then again, when you come up, there is a non-zero component that's going to the right. So you're stuck here in a cycle, and can never go upstream. So that's a good design. Okay. Any questions about this?
So because of the main question, what are the six different so we can not figure out language or to kind of like certain
What do these things do? I think there are boundaries of walls.
as boundaries that
So it's a cube with interior protrusions. This is a cross-section view of a tube, right? So it's not a smooth tube, but with these corrugations in there. Yeah.
yeah, that thing is obstacles
Yeah, they're part of the wall. Yeah, physical wall. Yeah.
like this.
Version is for the simple application.
Yeah, this is for single, just to demonstrate the behavior.
What is developed that's when who has a possible
The walls in this case, if you have a colony in your urine bag,
Which means you've actually placed the colony there. Okay. So yeah, it's very dilute in real systems.
because then people is germany without any bacteria. Some bacteria
yeah, they can grow it. On the walls, they can grow biofilms, and that time scale is much higher than what we're looking at here.
It's not going to take you 10 seconds to grow a colony of bacteria, but a single bacteria in 10 minutes has already went into the catheter tube. Yes, those things occur, but they're at a much larger time scale than what it takes for a particle to go upstream. Okay.
Also, this how much do we do in the
Inches. That's a great question. You have to do that. You have to do the computation to figure out.
so we
Yeah.
thinking it is not possible to do it directly from the body. It's like
No, you have to rest with the equations. You can do it analytically. Yeah. Unfortunately, there's only a number of you can count it. Only a number of cases where you have analysis solution.
But the equations are the same equations. You just have to solve them numerically to get the results, and that's what's done here. Okay.
Yeah.
I met yesterday also we were discussing drawing this edges was side.
Yeah.
In that equation where you said information that
Use the density gradient.
like for edges instead of skin. Like it's
The base geometry is something you specify. Right?
yeah.
Yeah. That's the geometry of the system.
Yeah.
You have to tell me what's the geometry, and then I can
So that
use my equations to compute it for the particular geometry you specify.
yeah.
Yeah.
So like geometry is manifested in that equation, the geometry is manifested in the
Because when you think about a partial differential equation, when you want to solve a PDE, you have to specify the domain. Right? The domain is your geometry.
okay.
And you can't, when you solve a PDE, you can't solve it without telling me what kind of domain we're looking at, right? Yeah, in addition, there's boundary conditions that's applied at these boundaries out of your domain that you specify. That's right. Yeah.
So that means Stephen
You can do whichever method you like. You can do find out and then find the volume, find the difference.
So long as you can solve the PDE, that's fine. Okay.
So that's what this
Yeah.
is saying. A constant plus A. And there are other mechanical balances. So the
Other
first one is
questions, comments.
stress balance on the surface. So it's the stress
Okay,
outside,
good.
Yeah.
stress
It's
inside.
like
No, that's okay.
Then you think that tangible
So in this case, yes. So what you have to do is more complicated than that. So you have to first solve for the flow field, because you have flow going into this tube. So that's solved by solving which I haven't talked about, the Navier-Stokes equations, using a finite element solver, and then you have flow field information there. Once you have that, you can do Langevin equation, Langevin dynamic simulations. Now, because you know the flow field already, which is solved somewhere else. Yeah. So essentially, as we were talking about this, so how much do you have to tilt these structures? So that's part of the design problem you have to do, which we've done, and I'm not going to tell you the details about it. But here's an experiment that we did. It's quite a busy plot, so let's unpack this slowly. You see two shaded regions, okay? The left is a design tube, which means it has these structures in there. The right is also the same. Oh, sorry. One sec.
hopefully most of
let's
them
look at the
is
left
separated.
region.
So there are
There's two
at least conceptual
columns here. The first is a smooth tube, which means that it's a regular catheter tube, okay? And then these columns here are the design tube with the corrugations. But in the left shaded region, the fluid velocity is 0. Okay, no flow, flow is turned off. In the right region, I still have two clusters. One is the smooth tube, one is the design tube. But in this case, there's a flow, particular flow rate that is comparable to what you get from these real systems. So now let's look at the left side. Again, keeping in mind that the flow is turned off. Okay, flow is turned off. And if you have a smooth tube, of course, when the flow is turned off, there's no notion of what is upstream or downstream, which means bacteria is going to go in either directions equally likely.
What is the relay percentage?
C, that's a label for the graph, but the y-axis is the colony count. So what you have to do is you at a location of the tube, you collect some bacteria there, and you culture them. Then you count how many are there to figure out how many bacteria is in the tube. So that's what we're doing here. So you say for the smooth tube, we have 3 columns here. So that's sampling the number of bacteria at different locations upstream. So, okay. So this one is the closest to the reservoir. Further left is more away. So in the absence of flow, of course, you would have bacteria going somewhere. So you will get them going up or down equally likely, okay? But when you have these corrugations, what you see is you get much less. And here's a zoomed in plot because you can see this. And if you compare these, at least 1 order of magnitude smaller. Why is that? That's because of the rectification. So I've deflected them towards a particular direction without flow, okay? Without flow. Any questions about that? So that's essentially an experimental realization of the theoretical model we talked about yesterday. So that's the left side. On the right side, the only difference now is I've turned on the flow, okay? Again, for the smooth tube, you're going to pick up bacteria, less so even further upstream, but still significant amount. In the design tube, that's way less. A few. What is what?
Design tube smashing.
That's the flow rate. Not going to tell you exactly what's the flow rate, but there's non-zero flow rate there. And if you look at the design tube here, the number of bacteria you get upstream is orders of magnitude lower, even compared to this case. So there are 2 things that's happening here. One is the corrugation, the rectification that's still present in the flow. The other thing that happened is because you have these corners in the tube, if you think about the flow that's coming in this direction, you would have sort of recirculation zones here. That will turns out also going to turn these bacteria downstream. So you get both these effects add up, and then you get much more reduction in the bacteria you get upstream.
And that's what
That's where?
and 2 minus 1, like
Here, yeah. It's, if you can zoom in and look at the inside there. Okay. So here's a summary of what we looked at here. So here's a smooth tube with flow. I'm gonna go upstream like this. Here's a design, but it's not tilted enough. I try to go upstream still, but there's a reduced slightly, not so much. But in this case, a bacteria comes up, it's going to be deflected downstream. Okay?
So what should make a critical angle of the state that
You have to do a simulation to figure out for a particular bacteria.
that bacteria comes up in reservoir?
Yeah, we don't know. Okay, it's a complex optimization problem. What you have to do is you generate a geometry, solve the flow field, solve the particle dynamics. You get the velocity, where they're going. Do another one, and then you explore your design space, and then you figure out where is the best in the space.
so we do this one is like the round mapping. So once this
Yeah.
put the value for kind of
So in general, regardless of this kind of optimization or real life optimization, you have only one thing you're thinking about. You just generate a random parameter space that you have, and you have an objective function here. It's just, I want to maximize the velocity going down, okay? So that's all you have to do mathematically. Of course, the details here is you have to solve the flow field equations, solve the equations for the bacteria to get that objective value. But in general, the way to do that is the same.
So we put like in the result that we get from solving the simulations.
Yes.
We get with one map exercise and everything.
Okay.
Then we put the values on the certain bacteria and one look at.
Yeah.
Then maximize the values.
Yeah.
That is how we get that, right?
That's correct. So it's not an easy task, but conceptually you can do it. And it is the point here. And what we did actually is we made use of machine learning to
reduce the number of simulations I have to do for these shapes. But nonetheless, that's not important here. Okay, so we did that, and then you can do this easily. Again, you can easily 3D print these catheters with these internal ridges, okay, and then characterize how they behave. So here's another interesting application of rectification. So here's a plant. So this plant is carnivorous, and it tries to catch prey. Okay, here's how the plant looks like. And here, you see these protrusions are the chambers that they're trying to trap prey. Here's the image, cross-section cut. What do you see? You have these, precisely these structures that's tilting upward. Okay, so what happens actually, these bacteria, these plants make use of the rectification to catch microfauna. So if you look at these are kind of particles, how they're migrating to these chambers. Turns out that if you can do an experiment where you have just that passive particles, you put it into this chamber, it's not gonna migrate to upstream, which is where they consume these things. It's gonna migrate much less than you have active particles, because for active particles, going this way is easy. Going down is difficult, so they get trapped there. And so that's an interesting observation that these plants make use of these physical principles that we've discovered. Okay, so that concludes our first lecture today. There's another plot here that I want to show. So here's the thing I talked about. So essentially we're looking at number of particles. So you can do an experiment where you replace the microfauna with passive particles. And what you see here is if it's motile, those are the microfauna they're trying to catch, you get much more particles in the chamber. Whereas if it's passive, much less. So there's a bias influx due to this rectified transport that we talked about. Okay, so that's it for the first lecture.